That's what operation shows repeated multiplication. Yeah, I want an operation. What operation could show repeated multiplication? Exponent, right? That's why the exponential equation is y equals a times b raised to the x. What am I repeatedly multiplying by in this equation? Not for this function, but for this equation, what would I have to repeatedly multiply by? B. B is raised to the x. B is that constant factor. B is what we're repeatedly multiplying by. So this is a quick review of what we've already studied. So what is A going to stand for? That's my y-intercept. So for this function, g of x equals, what's my y-intercept? 405 divided by 4, or fourths, times 3 halves, raised to the x. So Naisha, earlier you asked, hey, can I actually flip that and write it in this way? So someone other than Naisha, what do you think? Could I write it this way, Jacoby? Say again? Yes? Anybody else agree that we could write it this way? And I want evidence why from somebody else. Jayla? No one's going to talk. I'm going to start calling on people. Can we write it this way instead?
I think so.
You guess so.
I said think.
Say again?
I said think.
You think so? So what do you, and here's the thing, I just need to know why you're thinking that. Why are you thinking yes, we could?
I mean, all we did was swap it, so like, we still get the same answer.
So all we did was swap it, so we should get the same answer. Notice, could I substitute some values in for x and see if it gives me the right outputs? 100%. Lily Kate, were you agreeing that, or did you want to push back?
Yeah, I was going to say pretty much the same thing. Like, it's still the same thing being multiplied. It's just swap.
Okay, so it is still the same thing being multiplied. I will point out this is something we want to note. Think about it this way. In this equation, even though we've reversed the order, what's being repeatedly multiplied? And how do we know? How do you know that 3 halves is being repeatedly multiplied? Because the variable exponent. Right, so pay attention to that. The variable exponent is what tells us what's being repeatedly multiplied, because an exponent is the idea of repeated multiplication, which leaves the 405 divided by 4 is still the y-intercept. So yes, you can switch it, but notice that going back to that foundation of, well, what is repeated multiplication? It's that exponent there, okay? So those are details that we want to pay attention to. Hello? Not yet. Gotcha. No problem. All right, from there. Actually, questions. That is the end of that review. So quick little review. Help us remember exponential functions. Sweet. Good talk. All right. Moving from there, I should go ahead and stop that poll question. Should have stopped it earlier. Clicker would be helpful. So a couple of quick notes to help us get started. Agenda. This is very heavily rooted in both the bell ringer and what we're about to study. What is mathematics? Study patterns and relationships, especially with these inverse functions. We've already discovered a lot of functions built on patterns, and these inverses are very clearly connected to those patterns. So a couple of quick notes. Papers or books around the room. I'm tired of seeing books left behind. A lot of us are going to have to take the final, not a lot of us, quite a few of us have to take the final. You need your books with you. If a book is left in my classroom today, it is getting thrown out. If there are papers left in my classroom today, they're getting thrown out. Take your materials with you, okay? You need to study them. Retest. I don't usually offer a retest because the test is supposed to be the last chance you have to show me mastery of concepts. Some of us still need to take our test. If it is not taken by tomorrow, then the only option you will have is a retest, and I will be passing your test back tomorrow, okay? Quite a few of us need to consider doing a retest. Tomorrow I'm going to go over a couple of quick details to point out where some of us went awry. For example, when I ask you to identify the x-intercepts or identify the zeros, don't tell me how many zeros there are, tell me what the zeros are. Like, those are things that a lot of us miss details on. And so when I give you back your test tomorrow, I'm going to give you a sheet of paper that goes question by question to identify what day we went over that lesson, so that if you can't come into tutoring, you can watch the video on it, and what lesson it comes from in the book, so that you can hopefully go to your notes. You are not going to be allowed to start the retest until Friday. The reason being is, if you're going to do a retest, you need to actually take the time to study for it. Okay? If you're going to do a retest, then you need to take the time to study for it. I will be sending out my final parent newsletter this afternoon, / this evening, where I'll be letting your parents know about that retest. And quite a few of us need to consider it, because this information is not going to go away. A lot of the information that we learned is foundational to what you would take next year. So we need to take it seriously, even if you're not taking the final. You need to learn this information for the next class, and if you are taking the final, you need to review this to be ready for that final. There was a lot of us that definitely could have shown me more than we did. And I'll pass those back. I've already put the test in the grade book, and you can check those at a different point in time. Quick recap, inverse functions. This is what we studied for the last couple days. What foundations about an inverse should we already know? There's two major things that we have to know about inverse functions.
It's like, yeah, it's the opposite.
Have you ever heard me use the word opposite?
No.
No. So I understand why we're thinking opposite, and I get the idea, but remember, vocabulary matters in mathematics. When we say the word opposite in math, this is the only thing we mean. What is the opposite of 3? Negative 3. What is the opposite of negative x? X. The opposite only means to change that sign, right? To go from positive to negative or negative to positive. And it's because we're going to add and it creates a 0. So there's something about transposing with inverse functions, right? When we transpose, what are we transposing?
The y equals x.
There's something with the y equals x, but that's not what we're transposing. We transpose because of that y equals x. So we transpose. So the first thing you got to remember going into today's lesson, transpose x, which is also called my inputs, that's the domain, right? And y, the outputs. And what's causing us to transpose those inputs and outputs? Has something to do with that y equals x. Because we're reflecting over y equals x. Guys, if you don't have these final details down, you've got to know this to be able to continue with the rest of this unit. These are the foundations of everything. We transpose the inputs and outputs because we're reflecting over y equals x. That is what creates that inverse function. Transposing the x and y because we're reflecting over y and y equals x. By the way, go ahead and get your textbook out. We're going to do some small details. Jalen, do what we can. Keep our head up. So get out a textbook. M3-7 is the first lesson. I believe the next lesson started somewhere around M3-19, which is what we're about to get to pretty quickly, okay? Come on, M3-19. Now, remember, this is how we get the inverse of a function, but not all inverses are functions. What do we call an inverse that is a function? Or what do we call functions whose inverses are functions? Something like that. You're close. Invertible functions, right? We got to remember, guys, a function whose inverse is also a function is called an invertible function. And how can we quickly check to see if a function is invertible? Which one? So remember, the VLT refers to what?
Vertical line.
Vertical line test, right? So when I look here, This passes the vertical line test, but that tells me this relation is a function. What tells me if the inverse is going to be a function? The horizontal line test, right? Because the vertical line tells me that each input maps to one output. The horizontal line test though, right? If I check right here, that's one output and it has how many inputs? 2. So that's 2 inputs with one or with the same output. Which that's fine for a function. But what happens when I get that inverse relation? What happens when I get the inverse? Come on, inverse. You gotta know this right away. We transpose those inputs and outputs, right? So if we have 2 inputs with the same output, when we transpose, that means that I'm going to have how many inputs? 1 input with 2 outputs. Is that going to be a function? No. Right here with this horizontal line, I'm actually, with the inverse, going to have 1 input with 3 outputs because it hits that 3 times. Does that make sense, Hayden? So the horizontal line test is what tells me about an invertible function. And that's because we're going to reflect across what again? Y equals x. Hey, do you know what a horizontal line becomes when you reflect it over y equals x? It's going to become vertical line. Because remember, that vertical line test is how we check to see if a relation is a function. Okay? So those are things that we want to pay attention to. Hayden, do you not have your book with you today? Okay, grab it. Huh? Check to see if it's one of these books that got left over here. Make sure you take it with you, because I know that some people grabbed books yesterday and they didn't write in them, but they grabbed them to refer to in my 3rd block, I believe. And I believe they sat up in these desks. So that's one reason why we don't want to leave our books. All right. That covers everything. I will remind you, what is the pattern we recognized yesterday for the power functions? Which set of power functions are invertible? The odd degrees were invertible and the even degrees were not. And remember, that's because when I look here, negative x to the 4th, that's even. So I know the end behavior is the same direction. Leading coefficient is negative, so it has to be going down. Notice I'm just using my knowledge about end behavior and leading coefficient to figure this out. And when I look at that even degree, see how it fails the horizontal line test. Whereas the odd degrees will pass the horizontal line test. Is that the right one? No? Was U-bar in this one? Check this one. By the way, you know that you can access the textbook on the iPads, right? Huh? It's always been the case because you can go, I've loaded them on Schoology. You can also just go to Carnegie Learning, and instead of going to Mathia, there's an option for the textbook there. I bring that up because Bryson Prosser figured out how to write on the PDF with the iPad so that he took notes, started taking notes on his iPad. Is that the right one? Cool. So make sure you take it. Huh?
What page is that?
Great question. This was page 15, but we're jumping here to 19 now. So now we're looking at specific inverses, right? We're going to look at the square root function and the cube root function and talk about radical functions in general. I need you to hear me on this. These are the foundational lessons to get to really the meat of what we're going to study with something called exponential and logarithmic functions. So this to help prepare us for that next step, all right? We did talk about this yesterday with this getting started. This is a small detail. Remember the book, to find the inverse function, what does the book do first? They transpose first. And then they solve for y. What did I recommend to do instead though? Transpose last. Because I can look at it right here. What would I do to solve for x to find my inverse? What would I do to x to find the inverse? Right away, take the square root. And positive negative square root of y is equal to x. Remember, that very clearly shows me that what was the output has become my input. And then at the end, if you want to, you can transpose, but this is actually where I would start, where you solve for whatever the input is, and that input becomes your output. So I transpose at the end. It's a little bit more mathematically accurate, and it'll help you. And so this is where we left off yesterday. I should have gone ahead and graphed this on here. So remember, -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. That is my original function. What was that original? F of x equals x squared. And what notes did we write down yesterday to get the inverse of that f of x? So remember, this is on the next page. So that was to get the equation, but how did I get the graph for the inverse? There's two things that we should remember.
When you transpose, you get the same point.
Sometimes. When did you get the, because remember, you just brought up the key idea that we are going to do what with our inputs and outputs? We're going to transpose. So for the inverse, right, so for my inverse, what was -3, 9 becomes 9, -3. Notice, Lily Kate, is that the same point?
Wait, no,
Is that the same point as this one?
no.
I get 4, -2, 1, -1, 0, 0. That is the same point because the inputs and outputs were the same. So that was answering B is what you were thinking about. Some of the points, when the input and the output are the same, you get exactly the same point. And that's also because, remember, those points were on the line of reflection. And so we should already have this graph as well. And what can we draw in there to help us visualize that those are in fact inverses? Y equals x, right? Y equals x has a slope of 1, it goes through the origin. Notice I'm just quickly doing a slope of 1 through here. The more points you have, the easier it is to draw a line. I will also remind you, what tool do we have in class to help you draw lines? Rulers, right? If you want to grab a ruler at the start of class, you can totally do that. But we can very clearly see that that is that reflection now. 20, I believe? 21? In 3-21. Okay. Were you able to find it? And where we finally left off yesterday was that the domain was -infinity to infinity for y equals x squared. The range was 0 to infinity. And then what did we see for the domain and range for the inverse?
It's the opposite. So 0 infinity for every next one, infinity.
Okay, so let's think about that language, the word opposite. Do we want to use that here? No. So they transpose, so the domain and range was more what is a more accurate way to say it? They what? Starts with an S, they swap, they switch, right? That'd be a mathematically more accurate way to see it, or say it. So remember, if I'm asking for domain and range, you need to use that interval notation. Please notice that some of this practice with domain and range will help you go back and do the retest because some of the questions were about domain and range. So pay attention to this. A lot of what we do this beginning of this unit is going to help you be prepared for that retest. Alright, so just a couple minutes. I want y'all to look for the x-intercepts and the y-intercepts within your small groups. We'll come back together, so look for the x and y-intercepts of both the function f of x and the inverse of f of x. We'll come back together and have a whole class discussion about it pretty quickly. Okay, so work with each other to figure out what they're going to be. The x and y intercepts for the the function and its inverse. No, that's not what you want, because you want 2. what I would do is I would download it. Scroll through it to here, but find it in your downloads later. Here, right. There you go. Oh yeah, that was way easier. I didn't know where it was. There it is. Yes, sir. You have your book? That's the wrong book. You have volume 1? Okay. It's going to be better to have your physical copy because you can more easily take notes. That's what I will say. You're going to have to 30 maybe? Oh, that says 300, doesn't it? All right, so what are the x and y intercepts? Sorry, that took me longer than I meant to. X-intercept for f of x, what did we discover? By the way, that was honestly, with the most love in my heart, pitiful on the active collaboration. I heard very little talking. Come on, talk with each other, check in with each other, make sure we have this. X-intercept for f of x. 0, 0? How do we know that that's an x-intercept? Because the y is 0, right? 1 is where the y is 0, 2 is where it intersects the x-axis, right? Okay, what about the y-intercept here? Also 0, 0. Again, because that's where the graph intersects the y-axis. And more importantly, that's the y-intercept because the x value is 0. So what about x and y-intercepts here? Same thing. Because they're going to switch. Technically, this y-intercept becomes this x-intercept. And this x-intercept becomes the y. However, those are exactly the same point. So why did I make the note that the x and y intercepts are switching, even though they look the same? Because the reflection over y equals x causes our inputs and outputs to transpose, to switch, right? So keep that in mind. Now, here's what we need to notice. This is going into the next page. When we look at this inverse, that reflection across y equals x, is the inverse a function? No. And the problem with something not being a function is, if I ask you for the output when the input is 4, what's the answer? What is the output when the input is 4 for the inverse? Look at the graph or the table. The one option is -2. The other option is +2. So here's the thing, there's two options. Do we know which one is right? No. We want functions because we want one input to have one output so that we know exactly what it is. That's the problem here. We want one input to have one output. And so what we can do based on this information, notice it actually talks about it right here, 9 has 2 square roots because 3 squared is equal to 9 and -3 squared is equal to 9. But we're going to restrict the domain to values greater than or equal to 0. The inverse of the function is also called the square root function. So what they mean is this. What's the domain referring to again? Just the x values, all the x values, right? So we're going to restrict the domain, meaning the domain is no longer going to be -infinity to infinity. It's only going to be part of that. And so what I want you to think about is this. Okay? Talk with your group. I want you to think about that graph right there. And I want you to think about f of x. What part of f of x could I erase? That would restrict the domain. What part of f of x could I erase so that when I have the inverse, I still have every single input and output? It's just I won't have double the outputs, right? So I want to erase part of this graph so that when I reflect it, I would have a function. I want one input to have one output. So think about it. We don't have to know the answer right away. I just need you to think about, hey, what could I erase so that when I reflect across y equals x, I would get a function. So talk about it for just a minute or so. Think about what could we erase from this in order to for the inverse to also be a function? Let's make sure that we get the inverse in there, because right now you just have f of x, and we're gonna get there, yeah, so that's what we're looking at. What do we think?
Are you asking like what part of the shape?
So like if I look at the original f of x, I'm gonna have to erase part of it, which is gonna be that idea of restricting the domain. What could I erase off of here? Like, don't do it right now, we're gonna do it on the board. But what part could I erase so that the inverse is also going to be a function? And I want you to think about this. If you have an invertible function, what's a way to check if the function will be invertible? So think about that. Look at that graph, right? What could you erase so that you get an invertible function? Yes, ma'am. So I'm just asking, when I look at, okay guys, when I look at f of x, this original function here, what could I erase from this graph so that its inverse would also be a function? Okay? So right now, we know that when I reflect this over y equals x, that inverse will not be a function. So what could I erase from here so that when I do reflect, I get an inverse for the, or I get a function for the inverse? Any thoughts? Be careful with your graphing. That's negative 2, 9. It should be negative 3, 9. That's why it looks so vertical. It shouldn't be that vertical. Any guesses? Predictions? Huh? If you take one of the sides off, would that make it so that the inverse is also a function? So like if you take this off, would that be would the inverse be a function? What are you testing? Yeah. Marshall, talk with Jayla about that idea. What do we think? Just from that f of x, that parabola right there, what could you erase from it so that the inverse is a function? Just that one thing? Okay. What do y'all think? Left side of it? And so just be left to the right side? Think about more mathematical language, where would you stop erasing from? What do y'all think? Left side? Okay, why is that? Think about that language, let's update that language. So when you say it's going to make it horizontal, talk about that. What is Lily Kate referring to? So what do y'all think?
I don't know.
So you're going to erase
It wouldn't make it horizontal.
this left side is what you're saying? Why would you erase that left side?
See what this is like.
Well, what we're going to do is we're only going to have part of this parabola, and we want it so that part of that parabola is going to be invertible, so that the inverse is a function. So what would happen if I erase this part of that graph? Maybe. We'll talk about that more in a second, but think about it. If I were to erase that part of the graph,
Just
Would the-
part for both sides.
no, just because we're only looking at this parabola, right? So I'm only erasing this left side, right? If I erase that, look at what's left. It's just this part of the curve, right? Would that be invertible then? And how do we know? Okay. So that's an idea. Think about that some more. We're going to have this whole class conversation. All right. So I've heard a couple predictions. A lot of us are hitting on the same idea. I need someone from a group to share. And remember, guys, this right now is the learning moment. These are the foundations that we want to write about, we want to talk about. This should go on the next page near this idea. But what are we going to erase? The left side? Okay, so left side and stop at the vertex. I'm going to keep going. So erasing all of this. Erasing all of this, and I stop at that vertex. Okay, so Jayla, I heard you say something similar. Why? Ooh, actually, better question. I heard Jayla say this. Marshall, why did Jayla say this? Why did Jayla say that we're going to erase all of this and stop here?
Makes the inverse match.
Okay. Jayla, is that what you told Marshall about? Okay. So guys, we got to make sure we're communicating. When I walked away, it didn't seem like we communicated very long. Jayla, your responsibility is to make sure Marshall understands it. Marshall, your responsibility is, if Jayla's explaining things, we gotta understand it. We are a small group working as a whole, so what idea, Jayla, are you hitting on? That if we erase this, it's gonna pass what? That horizontal line test. That horizontal line test helps us determine if that function is what? It is inversible. What's that actual word? Invertible, right? Notice if I now draw y equals x here, and I sketch that inverse, then it's going to look like, whoops, not that point, that point. Now I just have this piece of it. Is that inverse a function? Yes. This is what we mean when we say restricting the domain. The original f of x had what domain? Negative infinity to positive infinity. This restricted parabola has what domain? Well, that's only the maximum. Remember, where's the minimum? The x starts at 0, and remember, if I can have that value, that's when I use a bracket. What's the maximum x? When we use the domain and range interval notation, minimum comma maximum. Do not forget that. So, if you had actually noticed right here in the book, what does it say to restrict the domain as? X is greater than or equal to 0. Visually, why is it? Because it's going to pass the horizontal line test now. So we know the inverse is invertible. So, now we should be looking at the next page in its entirety. Number 3, right? So, what would be the ordered pairs, plotted points on the function for the restricted domain and the corresponding inverse points? I think that they're actually referring back to here. So what they're talking about, I don't love this, but they're talking about this point maps to this point, here to here, these stay the same, right? So what they're referring to on that number 3 is going back to the previous page, drawing those dashed lines to connect the points on the restricted domain, right? So we're only looking at the restricted domain, we're not looking at the other set of points right now. So what are the ordered pairs that we connected? 0, 0 connected to 0, 0 connected. Right. 0, 0 mapped to itself. What else? 1, 1 mapped to 1, 1. Okay? Traylon, give me another point that we mapped. Give me another point from here that we mapped to the inverse. So we did 0, 0 to itself, 1, 1 to itself. Okay, so there's something with 4 and 2, but what was the original point? The x was 2, the y was... So what did that map to? 4, comma 2. Eliza, give me one more. Do you have, oh yeah, so you just have the book there. So remember, this is this point right here. Okay, the last one in the table. What's the last one in the table? 3, comma 9. So what did I have to map that to? 9, comma 3. Now, I'm going to ask us to extend this a little bit, meaning that we need to think about this. What would be the next easy point that we would map following this pattern? Don't forget we're looking at y equals x squared. So what would be the next point? If we continued this parabola and then continued this inverse, what points would we be looking at? Where did you get that from? Maybe, but my question, I mean, so start here, right?
It's like x squared.
X squared, right? So what is 4 squared? 16. So what would be the point that that maps to? 16, comma 4. That's the whole idea, right? Like we're looking at that inverse, we're looking at the inputs and outputs. What? What are the inputs and outputs doing? Transposing, right? And if we understand that we're dealing with y equals x squared, I'm going to square my x value. What would be the next point that would be easy to transpose for the inverse? 5 comma 25 would become, there we go, right? 5 squared is 25. The inverse, the square root of 25 would become, square root of 25 would be 5, right? So, don't forget, f of x is equal to x squared. So I have my input, I get my output. Now, don't forget as well, are there other points in here? Like in the middle of these? Yeah. Remember, to get a smooth curve, there's how many points? Infinitely many, right? Here's a point, and here's a point, but there's a point here, and here, and here, and here. So why am I only looking at these? Yeah, because they're pretty. I wish I was joking, but like, if you think about it, 1.5, do you really want to square 1.5? No, right? But 1 squared is easy, 2 squared is easy, 3 squared is easy. So I'm using pretty points, but there's still infinitely many between them. I could do 1.213 squared. It'd be hideous. I don't want to do it, right? There's still beauty within it. All right. So don't forget f of x equals x squared. And the inverse of f of x, the inverse function of f of x, why can I use this notation now? What does that notation indicate? What does that notation indicate? That the inverse is a what? Function, right? That's the inverse function of f of x. When we use that notation, that means inverse function of f of x. So what is the inverse function of f of x if f of x is x squared? The square root of x. But, remember we have that domain restriction where x is greater than or equal to 0. Because we need the inverse to be a function.
Is that a 1 after the fraction of the x?
Say it again.
Is that a 1?
Up here?
Yeah.
Yeah, remember that f superscript -1? Remember that's that notation for an inverse f of x. So B asks you to list the ordered pairs that you did not connect. Those were those points, -1, 1, -2, 4, -3, 9. Why did we not use those points? Because why? Okay, that was the left side we took away. What was the issue with that left side? Why did we have to take it away? So they become a function. What would this create if we transpose these values? What would be the issue? Why not? Tell me why. Because what? Okay, it's part of it. Go back to the definition of a function though. Notice if we include these points, the input of 1 has how many outputs? 2. If we include these points, the input of 4 has how many outputs? The input of 4 has how many outputs? 2. Okay? So why did we not include these points? If we included these, the inverse would have 1 input with 2 outputs. So it would not be a function. We need to notice and keep in mind the core ideas. Like what are we trying to do? We're trying to get an inverse function. Well, an inverse function only exists when each input maps to 1 and only 1 output. Go back to those definitions. Alright, so we're about to get some time to work at small groups. We'll go 2 small groups and come back. periodically. But what we're going to do is look here at this inverse function. Use the resources you have. Use all the information that you have up to this point. Notice we're still looking at what function f of x, x squared, but now we're only looking at what x values? Only the positives when x is greater than or equal to 0. You already have all this information. Use what you know to figure this out. One recommendation I might make is make a table before you start to try to graph. So work within your small group to identify what f of x is for that domain restriction, to figure out what the inverse function of f of x is, and figure out domain, range, x-intercepts, y-intercepts. Don't worry about 6 yet, because we haven't talked about asymptotes. So yeah, just do numbers 4 and 5 at vertical surfaces, and then we'll have a whole class conversation. All right? Let's get up, let's move to our vertical surfaces that we defined yesterday. Groups 5 and 6, if y'all want to work together, that wouldn't be a bad idea. When we have an inverse, the x and y are transposing because the function is being what? Reflected across y equals x. Guys, those are the two foundations for inverse functions. So, when I look at this, to help me out, I like to use a table. It just always helps me organize my thoughts. That's literally what a table does. So, what x values could I use? Because I saw one group starting here. Can I use those x values? Why not? X has to be greater than or equal to 0. Remember, we restricted the what? What are we restricting? What are the x values referring to? The domain. We restricted the domain so that the inverse is a function. We got to recognize this. We can't have those negative values. We started at 0 and went 1, 2, 3, 4, so on and so forth. Remember, guys, this literally is what we did on the previous page. Like if you look at the left side, or the left page, page 22, you see those points right there? No, 22. Ethan, 22. See those points under 3a? Right? What is 0 squared? 1 squared? 2 squared? 3 squared? And 4 squared? 16. Now I can't quite fit that on here, but here's my points. One thing I will point out to help you, I would probably use different colors for my function and my inverse. You have the boxes underneath the desk with colored markers and colored pens, so if you have your book, which you need your book, I would get those things out. Huh? I'll find wherever they went. So, the inverse function of f of x. So what would the inverse here be? 0. Whew, yeah. Those x and y's are transposing. That's it, guys. Don't make that complicated. And so, there's my inverse. And don't forget, what's causing that inverse, Grace? What's causing that inverse? There we go. The reflection across y equals x. That's what's causing our x and y to transpose. So Hayden, that pink inverse, is that pink inverse a function? Not yet? Why not? Why yes? The VLT, the vertical line test. If you're going to use the abbreviation, make sure you know what it means, right? Okay. I'm just saying because I'm going to ask you about it on test. So, vertical line test. So, every vertical line shows us that each input maps to one output. It's a function. And so, let's look at these answers. Domain and range. So, Shania. I told you.
I thought we were just playing.
I wasn't just playing. Nuh-uh. Being dead serious. Shania. why is the domain for f of x 0 to infinity, and why is the range 0 to infinity?
Because,
Notice that.
because, the,
Mm-mm. I need more.
because the, 2 zeros.
There's
Why?
something with that. Okay, something about the x and y.
And because when it, okay, so the domain, you see how it starts at 0, and you go up, that's positive. And then when you switch it, it still go up. Well, when you transpose it, it's still starts at 0, and then it still go up to a positive.
Okay, one thing I want to clarify is I'm asking about domain and range just for f of x right now.
Oh, I'm sorry.
Okay, no, you're good. So we're talking about this piece of the parabola. And so I'm going to reword this. I need y'all to hear or restate this. I want you to hear what Shania said, and I need you to think about it, see if you need to add on to or push back on the domain and range. So Shania said that for the domain it's 0 to infinity because it's starting here at 0 and going up to positive infinity. Why does she mean go to the right?
Yes, exactly.
So the x, you're missing a key, you're 100% onto it, but there's another detail. The x is referring to what, or what refers to the inputs? Not the x-axis, look at those keywords. Domain. Guys, we got to remember, if I'm talking about domain, I'm talking about my x values. So am I going to talk about going up when I'm talking about domain? No. It starts at 0 and it goes to the right. Because of that arrow, yeah, it's going up more than it's going to the right, but is it ever going to quit going to the right? No. So the domain starts at 0, goes to infinity. Okay? So what about the range then? Why is it 0 to infinity? Well, she said, when she was talking about domain, that it starts at 0 and it goes up to positive infinity, right? The lowest y value is 0 and it goes up for forever. So Preston, this is your chance.
Yes.
Preston, tell me, why is the domain and range for the inverse of f of x those values?
Because it starts at 0, and for domain, it goes towards the right.
Which piece are you looking at though?
Okay,
The pink one, the inverse. Okay, so it starts at 0 and it goes to the
the right.
right? Okay. So 0 to infinity.
And for the range,
Uh-huh.
it goes up towards the positive.
Okay, so it starts at 0, goes up to positive infinity, it never stops. But I will say this, I'm looking for something else. So there's more to it than just that. Why, if f of x is this domain and range, is the inverse this domain and range?
You transpose it.
So when we transpose, what's being transposed? The x and the y, the inputs and the outputs. So Jamarcus, this domain right here, is that my inputs or outputs? Domain is x, my inputs. And if I transpose in the inverse, it becomes my outputs. Note that, right? This domain, set of domain values became my set of range values. And what was my set of range values became my domain. We've got to notice that when we have an inverse, the inputs and outputs are what? Inputs and outputs are transposing, and the more plain English that you want is that they are switching. That's it.
So Shani, I feel like when your kids said their first word, you were like, now let me correct you in their language.
Probably.
Oh my.
Hard work pays off. You gotta learn. You gotta train it young.
Somebody come back and say mama. I'm gonna say mom.
Mother, no,
Yeah,
we will not use mother.
Now let me correct you, it's
Yeah.
actually mother in this house.
When we start learning mathematical vocabulary and academic vocabulary, I will be correcting them for sure. But also, it's at an age-appropriate level. The word transpose is an age-appropriate level because we're in Algebra 2.
What age?
Alright? The age that you're in Algebra 2 is when the word transpose is
Okay.
appropriate.
Yeah.
I will not be teaching my 5-year-old the word transpose because he will not be studying those concepts yet.
I mean.
Maybe I accelerate him a whole lot.
That kid's gonna be taking college
All
classes
right.
in elementary school.
So, number 5, we should have those answers down. Notice x and y intercepts is just this point. But a small detail to remember is This x-intercept is what became the y-intercept. And this y-intercept became the x-intercept. Even though they're exactly the same, we want to think through that because what's happening to my inputs and outputs? They are switching, and the more mathematical term is transposing, right? We want to pair those ideas together. I'm defining the ideas and constantly reminding you, here early on, transpose means switch. Z, you had some wide eyes there. What questions do you have?
He just look like
Don't be rude. Z, you were just thinking?
Yeah.
With that thinking, did you have a question?
No.
Eliza? Okay. One thing I do want to point out is this. This is not a term that we have established yet, but I'm going to go ahead and introduce this because this is going to matter for the next lesson. This word asymptote, this is a line or curve that a function,
Just say asymptote.
asymptote, that a function approaches at infinity. Okay? So that's the definition. I'm going to show you an example of this because you have actually seen these asymptotes with one type of function already. We just didn't talk about it yet. So a line or curve, yeah, M3-23. Okay. What type of function did I just draw here? That's an exponential. Can anyone see a line and want to come sketch a line that this function is approaching at some infinity? Just make a prediction. So it's not something that's going to touch, but it's going to approach it at some infinity. Any predictions? No? Okay. Right here, how about the x-axis? You see right here how the curve is approaching the x-axis? And it's going to keep approaching it all the way out to negative infinity in the x. It's never going to get there. But that's what we call an asymptote. So when I look at the range for this, what's the lowest y value for this exponential?
Oh.
Remember, it's approaching the x-axis, so is it going to go past the x-axis? So the lowest, it's approaching the x-axis, so the lowest y value is 0. Notice how I did not put a bracket here, because I said it's approaching. The y value on the x-axis is 0, but it's approaching, it never gets there, so it never actually equals 0. And then the maximum y value is infinity. So we're going to talk a lot about these asymptotes with the next lesson when we study the next type of inverse. Okay?
How do you know when to put a bracket or like?
So the way I always explain it is that you use a bracket when it's a number that is equaled or included. So like when we've been doing these zeros, do you see how the value 0 is actually there? So the x actually equals 0, so I use a bracket. Okay? Here, remember how I said it's approaching, but it doesn't actually get there. Because it doesn't actually get to the 0, I use a parenthesis. And then with infinities, you always use a parenthesis because you can't ever get to infinity. Right? It's going to approach it, but it's never going to actually get there. Yes, parenthesis is singular. So I say parenthesis when I'm talking about just one. All right. Well, we've already kind of established this. Hey, what's the relationship between the domain and range of a quadratic function and its inverse? The domain and range what? This is number 7 at the bottom of the page. What's happening to the domain and range? So they switch because, and I will accept that word transpose here. It's such a weird thing. The individual points are transposing, but it's causing the domain and range to switch. Okay, so it's just individual points that can be transposed. Okay, but because inputs and outputs transpose. The domain and range, what? Switch. Well, so remember what I just said was that the x and y, the inputs and outputs, those individual values transpose, but that's what causes the domain and range to switch. I'll check to see if you can actually use that word transpose for domain and range, but in the way I understand it, I don't believe you can. It's just those individual points transpose, causing the domain and range to switch. Okay. Guys, if some of these concepts are sounding foreign, make sure you go back and study here early on before we continue too far, because we're going to be building on these ideas for the rest of the unit. What are your questions before I continue? Or we continue? Ma'am, I always have these small ones up here if you need to grab one. Okay, so activity 2.2 is going to take on transformations of the quadratics. Notice in the function that we've been working with, we had f of x equals what? X squared. What do we have now? X squared minus 4. What did that do to this function? Huh? It changes the y-intercept, but it doesn't just do that. It does a little bit more. What else does it do? Say again. It does also give us, well, we already had some zeros, just not. It actually doesn't make it wider. So this point here goes down to here. This point here goes down to here. This point down to here. See how each of those points are mapping to these?
Yeah.
What's happening? Does anyone remember the word that causes points to move? So reflection, remember, means that it would go like this, right?
Transform?
It is a transformation. Translate. Literally what we did is we took this f of x and we translated it down 4. That's what we want to notice here, right? Every point was translated down 4 units. Oh, I didn't mean to already answer A, but how is g of x transformed? F of x is translated, how far? Down 4 units to get g of x.
Mr. King,
Yeah.
where do you get them points from, like?
So remember, Eliza, were you asking that question? Remember, we started with f of x equals x squared, right? So if you think about f of x equals x squared, negative 3, 9, negative 2, 4, I'm just squaring each of those x values. And because I've worked with this function enough, I know that, but also like that those are the points we just did for f of x in the last lesson. Does that make sense? Okay. So that's all it is. I took f of x, knowing that it's x squared. All right. So from here, all right. One thing I do want to point out, because this will help you see the next set of problems easier. What form of a quadratic could this equation be? What form could this be? What are the 3 forms of quadratics? Standard, vertex, and factored form, right? This could be what? This could be a vertex form. You could also see it as a standard form, but if you see this as vertex form, and that is the most useful, 1 times x minus 0 squared minus 4. Right? Notice I just included that understood a value is 1. What we would have to be subtracting here is 0. So what I would point out is, horizontally, the vertex is 0, negative 4. So the x did not change at all, but the y went down 4. That's why it was translated down 4 units. Okay, so it's translated down 4 units off of that. All right. Part B says, write the equation for the inverse of g of x and sketch its graph. What I will tell you is this. First things first, we should be able to sketch the graph for the inverse using the graph that's there. There's a couple different ways we can do that. But where did we see an example already of identifying the inverse equation? It's earlier in this lesson. You have to go back a decent bit. But it is within this lesson. I would go to maybe M3-20, I believe. You see that example there, where we are calculating the inverse equation. Y equals x squared, and then in the book they go ahead and transpose and solve for y. Remember, I made a slightly different recommendation. But we only have 5 minutes at this point. Say again. So, what I want you to do is get up to your vertical surfaces. I need you to actively work with your small group to figure out what that inverse equation is. So let's get up. We've got about 4.5 minutes left. Let's knock this out quickly. Eliza, talk to me over here, please. Come on, get up. Let's go. Let's move. Let's move.